Okay. Um, so yeah, I'm just going to pass to the PowerPoint presentation actually in a moment, because we have to say something more about this. In any case, so this is a very simple expression, but we are going to make it complicated. So we are going to see how complicated it can get. I mean, we would like to express it in a slightly more advanced mathematical form to make it simplified, right? That's what I'm going to do. But before that, let's just talk about the charge. And for this, I'm going to pass to, not to that. First of all, am I sharing the correct thing? Sorry, I'm sharing my screen, yes. So then I pass to this one, where I pass to the electric charge. So, I mean, this is the Coulomb's law. It's the force between two charges. And the question is, what is charge? And it's basically what we call as coupling constant, right? The idea in here is that these particles are interacting with each other with different types of forces. So for each type of force, there is a quantity that tells us how strongly that particle interacts with this other particle. And this quantity is the coupling constant, okay? So basically, the charge is the coupling constant for electromagnetic interactions. So that means if that coupling constant is zero, if the charge is zero of that particle doesn't interact with electromagnetic interactions. That's what it says, right? Like the, I don't know, the Higgs boson, for example, which has charge zero, or a neutral atom, and you can think of it like that actually, a neutral atom and neutron and whatever. Their coupling constant is equal to zero, and so therefore they don't interact with other particles with electromagnetic interactions. And similarly, if a particle has twice more charge than a second particle, then the first particle interacts twice more strongly with the electromagnetic interactions than the second one. All right, so as a result, the amount of the charge is a quantity that tells us how strongly that particle interacts with this particular kind of particular type of force. So the charge is the coupling constant for electromagnetic interactions. Mass is the coupling constant for gravitational interactions. And there are these additional coupling constants for strong and weak forces. So probably you have heard about these, but we don't teach them in high school or, I don't know, in these general courses. So as a result, these forces are a little bit more complicated. So as a result, we don't talk about these kind of coupling constants of them. But there are coupling constants for the other two types of forces as well. Okay, so this is what it is. And so, yeah, that's what I have explained, right? Large charge means, so I'm going to use my mouse, I think. Large charge means it couples strongly. Small charge means it couples weakly. Zero charge means it doesn't interact. So that's also gives us a method to measure it. You just interact with it and then see how strongly it interacts with you back. And in this way, you basically measure the coupling constant. Right, that's basically what it is. And sometimes we use the word coupling constant to describe it. So the unit is coulombs. So in SI unit, this is the fourth base unit of the SI system. So after kilogram, meters, and seconds, this is the fourth one. And so as a result, this is one of the fundamental units. So in the SI unit system, there are 3 more units, but these are something that are completely unnecessary units, right? One is the unit for temperature. Temperature could equally be well measured by the energy unit, by the energy dimension actually. There's this mole unit for the amount of substance, and there's something called for describing the brightness of light, it's the candela unit. The other 3 units are completely unnecessary, just you can forget about them. But this is this is one of the essential units. So there are therefore 4 fundamental units, and unfortunately there are many derived units that is derived based on the coulombs, and we use them frequently in our daily lives, the amperes and volts and things like that, ohms, Teslas, Henrys and things like that. Usually we don't actually immediately understand their expression in terms of this Coulomb unit, unfortunately. So that's the difficulty with these units. So there are so many units that you have been using frequently. You don't really quite clearly see the connection with this base unit. So the Tesla, for example, I don't know, nobody can remember that unit, like Newton second per Coulomb meters. This is quite difficult. But in any case, that's one of the difficulties that you're going to face sometimes when you're canceling units. So in any case, so that's a thing. So there are actually 2 other properties that's kind of important. One of them is that it is conserved, right? Charge conservation means if you have a system, then the total amount of charge within that system doesn't change with time. So as a result, in the hydrogen atom, for example, there's the charge of the proton and charge of the electron. Their charges do not change with time, but also the total charge does not change. So unless there is an extra particle moving to your system, in which case it's not a closed system, we call it an open system. If there's an additional charge going into the system, in that case, the charge may not be conserved. But otherwise, if there's no particle exchange with the outside, it turns out that the charge is conserved. And the question in here is, why is it conserved? So, yeah, yesterday we have been in a different course. I have been talking about these kind of things. So there are usually no accidents in physics, in nature. Nothing happens accidentally. So it's not possible that there's a conservation law of charge, but there's no explanation for it. That's not possible. So there has to be some reason why the charge is conserved. Okay, so at this point, I'm just going to tell you what the reason is. But let's remember this. I have talked about this in the previous semester. There is something called Noether's theorem. It's like, it's a theorem that she proved in 1918, but this is one of the fundamental theorems that we physicists use. Basically, we relate every conservation law to some kind of a symmetry of nature. And a symmetry of nature means that there's some kind of a symmetry transformation, and under the symmetry transformation, the laws of physics does not change. So we know that, for example, the laws of physics does not change with time. So whatever the laws of physics is at the Newton's time, we still have the same laws, right? The laws do not change with time. And we basically express this as a time translation symmetry of the laws of physics. And somehow, by Noether's theorem, you can show that this implies some kind of a conservation law, and the conserved quantity is the energy. So that connection is easy to establish for your level, but this is something that, I mean, we should always keep in mind. At some point in quantum mechanics, for example, or when you take advanced classical mechanics, you're going to see the connection between them. You're going to see why the time translation symmetry implies that the energy is conserved. But that's, I mean, that's after learning some advanced mechanics, right? But right now, all I can do is that to say that there's some kind of a connection between these two, right? There is also space translation symmetry. So the laws of physics doesn't change from here to there. The same laws are valid in Istanbul, as well as the laws in Ankara. They are the same. So the laws of physics doesn't depend on where you are. This implies that the linear momentum is conserved. And then the laws of physics does not change with different directions. All the directions in space are the same, equivalent to each other. So that implies rotational symmetry, and this implies that the angular momentum is conserved. So we have seen all of these three conservation laws in the previous semester, and they are somehow related with the fundamental symmetries of the empty space itself, of the space itself, right? That basically these are all the only geometrical relationships, symmetries of nature. And these are the only three mechanical conservation laws. We don't have any additional conservation law in mechanics, right? Only these three. But apparently, when charge is concerned, it appears that there should be some kind of a symmetry that is related, that somehow implies that the charge is conserved, right? When I say why charge is conserved, that's what I'm asking. I mean, there should be some kind of a symmetry reason why the charge is conserved. Unfortunately, that symmetry is not something which is easy to understand because you have to do quantum mechanics to be able to understand this. Even with quantum mechanics, it's not easy to see why these are related with each other. So this is a quite advanced topic. So I'm just adding this as an additional information. So there's something called a gauge symmetry. When you hear some particle physicist talking something, you have heard that these two words actually, the gauge theory and things like that. And they also talk about symmetry a lot. There's symmetry breaking and things like that. So apparently there's something called a gauge symmetry. So in quantum mechanics, this corresponds to some kind of a invariance of the physical laws under the change of the phase of the wave function or something like that. As I said, it's quite complicated. Even if I explain it, you're not going to understand anything. Even if you understand it, you are not going to make this connection why the charge is conserved. But in any case, we know what the reason is, or we think that we know what the reason is for why the charge is conserved, right? There's a good reason for it. And yeah, I hope that there are no questions. The second one is that the charge is quantized. And basically it means that the charge of every particle is an integer multiple of a fundamental charge unit. And we can actually see it for the case of the charge of the proton and the electron. Basically, the charge of the electron is exactly equal to -1 times the charge of the proton. And there is no difference between these two, which means if you form a hydrogen atom, for example, the total charge of the hydrogen atom would be equal to 0, exactly equal to 0, right? It's not just small or extremely small, it is exactly equal to 0. So, of course, we cannot experimentally verify that this is exactly equal to 0. We can only place some upper bounds, but I couldn't check the literature for this. I know that there are some people who try to put some upper bounds on the charge of these hydrogen atoms, experimental upper bounds. But in any case, we know that the bonds that they place on is extremely small, like 10 to the minus 20 or something like that. So as a result, there's some kind of a support from the experiment side that, yeah, it is, the charge of the electron is exactly opposite of the charge of the proton. And so therefore, the charge of the neutron is also exactly equal to 0. And charge of the other particles, like, I don't know what the other particles are, the pions and things like that, or the charge of the ions, the molecules and things like that. These are always integer multiples of that fundamental unit. Okay, so all particles have charges n times e, where n is an integer. It can be a negative integer or 0, that's possible. But there's some kind of a fundamental unit of charge in here that I always show with the letter E. And the question is, why is it quantized? There should also be a reason for that. All right. So this is a difficult question, but later I'm going to explain this to you. So there's also, we suspect that there is a reason for it, all right? But this is a little bit advanced topic, but I think we don't have it in here. No, I don't have any additional things in here. But in 1930s, a physicist named Dirac was able to show that if there's some kind of a hypothetical particle called magnetic monopole, then we can explain why the electric charge is quantized, right? There's some, again, this is quite advanced. It has something to do with quantum mechanics. But it appears that there is also a reason why the electric charge is quantized. And this reason might be the existence of some hypothetical particle that we call as magnetic monopole. Let me try to explain it like this. I think I'm going to get out of this. So that's something else, that's extra, right? So we know that each magnet has this north pole and a south pole, if you remember. And so as a result, they produce a magnetic field like that. So the magnetic field lines are going from north pole to the south pole, something like that, okay? And I think you have learned that when you break a magnet into two, when it breaks, you cannot separate this north pole from the south pole because new south pole and north poles appear in here. So new poles somehow appear in here. And so as a result, the magnetic field lines in here would be something like that, okay? So as a result, by breaking a magnet, you cannot separate the north and south poles, but they, because somehow the new poles appear. So apparently every magnet has a north pole and a south pole somehow located somewhere on the magnet. So every magnet contains both poles. And so as a result, a magnet is essentially a dipole that contains two poles. So it's a dipole. We will talk about these later, all right? But these magnetic monopoles are particles that have only one type of a pole. So that's a magnetic monopole. As I said, I'm going to talk about these. So if we had this kind of a particles, in that case, that would produce a magnetic field lines, and then, yeah, it would be something like that. Or we might have a magnetic monopole, which is composed of a south pole only. In any case, none of the particles, elementary particles that we know, have a magnetic monopole like that. I'm sorry about that. It's just the opposite way, right? In any case, none of the elementary particles that we know, electron, proton, quarks, and things like that, they don't have any magnetic charge. So as a result, we don't know if in nature there's really a magnetic monopole or not. And so as a result, we are not sure whether the Dirac's explanation is the correct explanation for why the electric charge is quantized. So that's one of the mysteries of the nature that we haven't solved yet. And we don't know what will happen, because it's just if there's such kind of a particle, then that's something that has not been discovered yet. But it may turn out, it may be created in some particle collision experiments in CERN, for example, or I don't know. We can observe it from cosmic rays, and I don't know. It can be discovered at any time, actually, but we cannot say anything about it right now. Right? There's this kind of a connection in here with something else, right? So as a result, this is one of the things. I think in here I try to explain that for some elementary particles between proton and neutrons, the quarks apparently have these fractional charges, like 1/3 of the elementary unit of charge. But this is not really against what I have said about the quantization of charge, because you cannot observe a single quark alone in space. It's not possible. So as a result, these particles are not free. So you can only observe 3 quarks in the same place, well, within a proton or a neutron or some other hadron, actually. So as a result, you can only observe the charge of 3 quarks together, and apparently the charge of 3 quarks is always is an integer multiple of E. It's possible also to observe a quark and an anti-quark, in which case so we don't actually violate that rule in there. So as a result, a lot of people actually still believe that the charge of the proton or the charge of the electron, whatever, this E is the fundamental unit of charge, and there's no smaller fundamental unit. Okay. So that's one thing in here. So that's two important things, 2 important properties of the charge. It is conserved. So the electric current has some of these nice properties. It just basically carries charge from one place to the other one, the electric current is. So it is conserved and it is quantized. So these are the 2 fundamental properties of charge that we had to explain at the beginning. Okay. Let me then finish this. I don't know if you have any questions. No, I believe. So then let's start with this. So this is the electric force. So as a result, the electric force is, sorry about that, is the force between 2 particles that have charge. So only particles, if both particles have charge, they can apply some electric force to each other. However, some particles like neutrons, even though neutron has total charge to be equal to 0, it has a total charge 0. Sorry about that. I think I'm going to raise this. But neutron is actually a composite particle. It's not a fundamental particle because it has 3 quarks in it. So it has 1 up quark and 2 down quarks. And if I remember correctly, the up quark has a charge of plus, this has a charge of plus 2/3 of E, and the down quark has a charge of minus 1/3 of E, and this one too. So in any case, the total charge is 0, but still, I mean, these particles are within a neutron, they are moving around. And so as a result, there is some kind of an internal charge distribution, some electric charge distribution inside neutron, okay? So because of that reason, a neutron may still interact with some other charges outside, but it's going to interact weakly, but it only interacts because it has some internal structure, right? That's also one of the common themes that we are going to stress on. I mean, there are things like, for example, the helium atom. For example, it has like two charges, two protons in its nucleus and two neutrons, and then there are two electrons in the orbit around. So I don't know how to draw these. There are two electrons in orbiting around it. So there are these charges in there. Again, total charge of the helium atom is equal to 0, but still there's some kind of an internal structure within it. Okay? I mean, internal charge distribution within it. And so as a result, if you have like two helium atoms next to each other, they will still apply some kind of a force to each other, right? Which is an electromagnetic force. It won't be as strong as the force applied between two ions. It will be very weak, but it will still be strong. So, sorry about this. It will still be non-zero. So two helium atoms will actually apply some attractive forces to each other. So there will be some forces. So these are actually weak forces. They are usually called as van der Waals forces. We are not van der Waals forces, right? I know that in chemistry courses you have learned about these, but in any case, on a molecular scale, these are important because, I mean, if you have liquid helium, for example, this is the force that's responsible for keeping all of the helium atoms together, right? So in a typical liquid too, when the molecules are neutral, there are still some forces between the atoms. So as a result, something is charge neutral doesn't mean that it doesn't interact with the other charges. It only means that it interacts weakly with, especially for molecules. It only interacts weakly with other charges or with other molecules. Right? That's one of the things that you should keep in mind. But we will talk about some part of these kind of forces later. Right? But let's then go back to this. Again, two particles with charges. So we will start with the simplest one. So we have the Coulomb's law. Let's start with this coefficient in here. This Ke in here is like 9 times 10 to the 9. And the unit is, I just write down the unit by just looking at this formula. So it's Newton meter squared per Coulomb squared. This is approximately, of course, it's not the exact expression. I think the exact expression is well defined. No, it is measured. Sorry about this. So there's some kind of a change in unit system in the 2 years ago. So as a result, I don't remember which unit is defined in which way and which of the fundamental constants are measured and which of them are defined. So I know that the speed of light is defined right now, but I don't know what happens with this one. In any case, so as I have said, I'm going to make things complicated. So as a result, instead of writing this coefficient as Ke, I just write it as 1/4 pi epsilon 0. The reason is that if I use this symbol, in that case, some of the formulas that we are going to see later will be simpler. Starting with the next chapter, right? In this chapter, it appears like you're writing an extra 4 pi in here, which is completely useless, completely unnecessary, it will appear. But in the next chapter, we are going to see Gauss' law, in which case it's going to be simpler to use this epsilon 0 than the other ones. Right? That's the only reason. Here, epsilon 0 is called the permittivity. empty space. What's the meaning of that word? Well, it is derived from some English word. So it kind of explains how the empty space permits some electric fields pass through or something like that. I don't know. I don't care. We don't care actually. So we don't understand this constant by just looking at that word. So I'm basically treating that the word is completely meaningless, but it's still a word that we have to use to describe that constant. And so as a result, I'm using that word, all right? So it has no meaning at all. So we have said that it's the permittivity of empty space, and sometimes we say that it's the permittivity of vacuum, empty space. So that means, I don't know, so there are things like, for example, the permittivity of some materials, permittivity of, I don't know, let's say some wood or water or some material mediums, so have some permittivities as well. Yes, there are, right? So we are going to see this later on. So every medium has some kind of permittivity. We will see later, okay? I will describe these, but right now we will be using this epsilon zero all the time, and we are just going to call this as the permittivity of the empty space, okay? So the fundamental constant is basically is expressed like that. I think epsilon zero has some value, but I cannot write it down from memory. So it's like 8 point something times 10 to the minus 10 or something like that. 10 to the minus 12, I think. But in any case, whenever I need to use the value of epsilon zero, I always convert it into this coefficient in here and then insert in that value. That's basically what I do. All right. So therefore, Coulomb's law. So this force in here is therefore 1/4 pi epsilon zero Q1 Q2 divided by R squared. Right. There is another thing in here, additional thing. So we say that F is attractive if, let's say it like this, for unlike charges. Meaning that Q1, Q2 product is negative, basically. And the force is repulsive for like charges, in which case the Q1 and Q2 have the same sign, and so therefore their product is always positive. Right, so we usually express it in words like that. So as a result, at different situations, we understand whether the force is attractive or repulsive by using English like that. But I would like to actually change the mathematical language that I used in here so that I don't need that language in here, right? I don't need to use English words to describe the direction of the force. For this reason, I'm just going to introduce some mathematical tools, right? So this is one of the things that I'm going to use a lot. And so as a result, I just describe it in here. All right. So this is something that I call as the, well, let's just do it like this. So I'll be basically placing one of the charges at the origin, and the other charge will be somewhere else. So I'm going to have some kind of a reference frame like that. So there is an origin in here. Okay, but for the time being, let's just forget about about the physics. I'm just going to describe a mathematics in here. So suppose that I have some point in here. I have some point P. And basically, we will talk about this the distance of that point to the origin. So let's say that P has the coordinates x, y, z, right? So I'm going to describe R as the radial distance of that point P to the origin. So this is the radial distance of point P to origin. It's always the origin. Okay, so this is a distance, but usually in some certain problems, we would like to describe this some kind of a coordinate. And as a result, we think of it as some kind of a, I don't know, radial coordinate. It is quite similar to the Cartesian coordinates, except that it's not Cartesian, right? It's just a slightly different, distinct from the Cartesian coordinates. But it's like some sort of coordinate, actually. So in any case, we know that there are unit vectors along the x direction and y direction and so on. So, sorry about this. This is J, and sorry, this is J unit vector, and that's K unit vector. I mean, we have used these unit vectors a lot in the past for expressing vectors. I'm just going to introduce this fourth unit vector in here. So that's the radial unit vector. Okay. So let me write it down like that. So I'm going to pass to white color again. So this is the radial unit vector. It basically points in the direction of the radially outward direction. So let me say it like this, points in the radially outward direction. Okay, basically it points along the direction in which this radial distance increases. So points in the direction in which R increases. So this is just like the this unit vector in here. So some people just also call this as the x unit vector, this I unit vector, whatever. That's the unit vector associated with the coordinate x. It is pointing along the direction where the x coordinate is increasing. So it's along that direction. So as a result, if you consider R as the radial coordinate, then this R unit vector is pointing along the direction in which this coordinate is increasing. Okay, this is just like the IJK unit vectors, except that it is associated with a coordinate which is not a Cartesian coordinate. Okay, so that's one of the concepts that we use a lot, and especially in here we use a lot, especially for describing these electric and magnetic fields. So this is how we use it. So remember, we had these two charges, Q1 and Q2. Okay, so suppose I would like to find the force on the charge Q2. What is it? That's not a good expression, actually. So let me call this as F2. I need to write down an expression for it, but I need to write down an expression for it that's also correct as a vector expression. Okay. So what I do is this. I think I'm going to use a yellow color in here. So first, I place the first charge at the origin of a coordinate system. So let's say it like this. Place Q1 at the origin, in which case you're going to describe the distance of the other charge from this charge by the radial coordinate, right? So this is then the radial coordinate in here. That's okay. We still have this radial unit vector along that direction. We are saying that this force is equal to, is given by 1/4 pi epsilon 0, the product of the charges let me write this correctly, divided by r squared times the r unit vector. All right? In that case, irrespective of whether the charges are positive or negative, then this formula is correct at all times. So you can see that when both charges are like, right? If Q1 and Q2 have the same sign, if both are positive or both are negative, then their product is positive, in which case this is a positive number. So as a result, like charges imply that this F2 formula gives you some positive number in here multiplied with the R unit vector, in which case the force applied on this, this charge Q2, let me use a red color for that, right? This F2, in that case, is in the radially outward direction because it's in the same direction as the radial unit vector, which means we have a repulsive force in here. So that's repulsive. Okay. In a similar way, so if you have unlike charges, this force expression is going to produce a negative coefficient in front. So this number would be negative, in which case the vector will be pointing in the radially inward direction. The force vector will be pointing in the radially inward direction. So as a result, this will lead to an attractive force. Okay, so as a result, in lots of different situations, we don't actually analyze the problem depending on whether the charges are like charges or unlike charges. We always use the same formula. And I mean, this is for the symbolic manipulation, of course. We always use the same formula and somehow cover all possible cases with the same formula. Right? But to be able to do this, of course, we have to use this construct called the unit vector, the radial unit vector. Okay, so in any case, what if you want to express the force applied on the charge Q1? In that case, everything have to start from the beginning again. So you have to place the charge Q2 at the origin. You have the radial coordinate, and then you have the radially outward unit vector along that direction, pointing like that. Whatever, you have to repeat the calculation again and so on. So there is this kind of an awkwardness with this notation. So as a result, for computing different forces, you still have to change the origin a lot. But apart from this, this is going to be useful later for, especially when we are talking in the language of fields, actually. So as a result, this is going to be useful. I think I'm going to come back to this and say something more about this notation in here. Okay, so let me stop here. Tomorrow I'll talk about the electric fields and then start with some more complicated problems. Okay, so let me finish it in here. So the things that I'm going to do with these videos is going to be the same. So I'm going to place them on YouTube, and I'm going to place a link of the master playlist and the chapters playlist. I don't know where I'm going to place these though. So let me think about this, all right? So let me stop here.